morning. So, before we begin, since it's just us, feel free to interrupt me at any time, ask questions along the way. Let's try to make this useful for you. By show of hands, have you heard of Waku? Yeah, awesome. Logos, graph, take the mic. All right. All right, so we know what Waku is. Do we know what Logos is? IFT? All right, what we'll do is we'll focus on Waku, but we'll also focus at the ecosystem around Waku. And today's route, and this is 35 minutes, we'll go over why Waku, a primer to what Waku is about, and the current projects and the integrations that Waku has built around it. We'll build a simple app. It's going to be a stepwise app that we're going to build, and then we'll wrap up. And then the goal for today's workshop, or a rather presentation, is to leave with a Waku client run-in. Just for somebody who does not know what Waku is, it's a libp2p-based gossip sub message bus. What it does is it's a gossip sub network. So each node in the network gossips the message further. And then the idea is that from the moment it leaves the client, it gossips around in the network and then it is received at the other end. And this ensures a few this ensures a few characteristics that we'll build upon. How it works is it's a simple pub/sub-based architecture. So the concept of content topics is derived or implemented. And these content topics can be seen as application-level content topics. It runs everywhere. So there's a light client implementation for resource-restricted devices. There's also a full node implementation for devices that might not have enough resource, or that have sufficient resources. And in a line, it's a secure, bandwidth-aware, and chain-agnostic messaging transport. The protocol stack looks a bit like this, where we have Relay, which is the real-time gossip network. This is also the full node implementation of the network. Then we have the store protocol, which helps with history retrieval. There are some constraints around the history retrieval. Waku is not primarily a storage layer. It is an ephemeral messaging bus. So history is restricted to a month. Then we have filter and light push. These two protocols go hand in hand. Filter is the subscription part of the pub/sub, where you subscribe to a particular content topic. And this primarily helps with resource-restricted devices. So think of filter and light push as a substitute for relay. For example, if you want to run Waku on a device that does not have enough resources, maybe internet bandwidth is limited, perhaps you want to save some battery because relay is expensive to run. So you would opt in for filter and light push, which is filter is a replacement for the subscription part, and light push is the pushing part, the publishing part. Then another thing we have here is RLN. RLN stands for rate limiting nullifiers. And it essentially helps a decentralized network like Waku with spam prevention. In an anonymous network, spam can be a hard problem to solve. And thus, RLN is essentially attaching a proof of your identity along with the message, and then sending that entire message, which also composes of not only the actual message, but also the proof of your identity into the network. All right, the why. The why is, and this is derived from just general decentralized architectures as well. With centralized architectures, we have a single point of failure, of course. And here we have, since we have distributed the trust into multiple actors, there's a permissionless mesh. Then we have, there's also IP-linked metadata that is attached with centralized APIs. Scaling is, with centralized APIs, you want to go vertical, but with Waku, you already have a network that's horizontally scaled. And it is censorship resistant by design. All right, so what is it? Just a recap is Waku's a drop-in transport. So any sort of JS, TypeScript app, that infrastructure that you might want to build that requires communications between any sort of actors, be it client to client, node to node, client to node, you can just use Waku as a transport layer. It is a message bus. It works in any TypeScript stack. We also have more implementations. We have bindings available in C. We have bindings available in Rust. We have a NIM SDK. I'm not sure how many of you have heard of NIM at this point. And we have RLN v2 already deployed on testnet. RLN v2 is essentially our way of introducing rate limiting nullifiers into the network, and all messages that are sent into the production network for Waku has a proof attached. So there is spam prevention, and then the spam prevention works in a way where you're allowed, every identity is allowed a certain number of messages per epoch, and epoch is a way to say that, okay, X number of messages per n minutes is how we define that that rate limiting. And then we have works in incentivization for a year now, and it's all open source. Waku's open source. All discussions are open source. So feel free to, if you're interested, it's on the forum. It's on forum.wac.org, if I'm not mistaken, but I'm sure a quick Google search can find you the right forums. All right, so building upon where it actually runs today, and I could only talk about so many projects. So Status, have you all heard of Status? Status. So for people who don't know, Status started a few years ago, about 2017, and it's today it is a private communities like Messenger. It's a social fi, but also it encapsulates a larger part of what we want a full stack social fi product to look like. So it's got an inbuilt wallet, it's got a browser, it's got communities, Discord-like communities, and we'll talk more about how Status and what Status is in the next slide. Then we have Portrait and Open Internet Protocol. Portrait is an open internet protocol, is a self-sovereign reputation layer for which is decentralized. Railgun, have you heard of Railgun? Railgun. So Railgun is a ZK-based private DeFi that essentially masks the transactions that are being sent into the network, so not everybody gets to know what you're sending, who you're sending it to. And GraphCast is a project by the Graph team. It is their off-chain indexer network that is used by the Graph protocol for indexing, and Waku is used for this, for the communication, the coordination that these off-chain indexers need to do. So for Status, as we talked briefly, Status is a private messenger. It's a wallet and a Web3 browser, and it supports both light implementation and the full node implementation. And the mission is that communications should be censorship resistant, and the metadata should be minimally leaked to other recipients or to the network. And this is the infrastructure that this is built upon. One of the key infrastructures is Waku. And then there's a storage layer, which is Codex. And this is all incubated by Logos, the parent org. What does it look like? So for the node types, we have both full nodes and a light node implementation. So even within mobile, you can choose to run a full node if you so want to, but it is not recommended. It is recommended that you run a lighter implementation so as to save bandwidth and battery. There are some key topics used. Key topics are essentially the content topics that the application uses. And X3DH is used, the encryption scheme is used for negotiating 1:1 secure channels. The protocols that it uses are, so it uses Relay for the full node implementations, filter and light push for the light node implementations. As we prior discussed, filter and light push is essentially a substitute for relay in a bandwidth restricted environment. And then store is just for some querying of historical messages. And then X3DH is used for negotiating encryptions. And then for spam protection, we use RLN relay. RLN relay is a fork of the relay protocol along with RLN, rate limiting nullifiers, which are, we discussed this. RLN is attaching a message, is attaching a proof of your identity along with the message into the network so as to realize that, okay, how many messages has this identity sent in the last X number of, in the X last N minutes, for example. Yeah, the network diagram is simplified, but what it looks like is on the left is mobile or any device that you have. For example, it could be a full node desktop, and there's a network of Waku nodes that help gossip the message that is sent by the device, and then so the message is sent into one node, and then it further gossips it to another node, and so on, and then it is sent back to whoever is the recipient of that said message. Now, the developer takeaways here is it is a browser, mobile, full node, whatever device. It's a friendly out-of-the-box solution for a drop-in transport. Status has it is analogous to how we see communities or servers in Discord, but completely decentralized. And it is in beta. It is out for download, so you can go try it. And you can self-host your node. So any full node that you run with status is itself a node. You're a node yourself. So you're helping protect the network at the same time. For Portrait and OIP, Open Internet Protocol, Portrait's the reputation layer. And the way it works is it uses signed JSON objects and it sends those over Waku. They use smart contracts, they use the blockchain for storing these CIDs for these JSON objects, and CIDs are content addressable, identifiable something. CIDs are essentially a hash for where what your data stands for. And Open Internet Protocol is the umbrella specification that Portrait is built upon. So Waku here is the default networking transport for all of Portrait. And of course, for OIP, it is only a recommended practice because OIP is a spec. And OIP decouples the messaging from the storage and from the on-chain logic. So Portrait's the reputation layer, OIP is the general stack. For the scope, Portrait's got profiles and nodes, but OIP has decoupled the messaging from the storage from the chain. And Waku's role in Portrait is it is being used as a full transport, but for OIP is a recommended baseline. And the takeaways here are similar to statuses, where it's a drop-in transport. It's easy to use it as a caching layer if you don't have if you don't require high reliability on storing your messages. And then of course it's verifiable, so they have the CIDs on chain, and then it is verifiable with signatures that are sent into the Waku network. For Railgun, Railgun's a zero knowledge based layer for shielded ERC20 transactions. So any tokens that you might want to send that want to be shielded, that you don't want to be public. Here, the community broadcasters pay gas, and the Wallet SDK is used to not only discover fees, but also for the transactions that are sent into the network. They use the light nodes, but also use the full node implementation, which is NWaku, as the broadcasters, which essentially pay the fees. They use all the protocols and store here. The store protocol here is opt-in. And to send a private transaction in the client is essentially just 10 lines of code. The entire user experience is gasless, and it horizontally scales. So you can keep adding broadcasters into the network. For GraphCast, it's an off-chain gossip sub for the Graph's indexers. And Graph has a concept of radio that embeds Waku. So there's a registry contract on chains that is used for identity. And then that identity is used to send all the radios, which is used for the communications between two indexers. So radio is a message that is used to send between indexers. It's an abstraction over Waku and the blockchain's RPC calls. And radios are app specific, the concept of radios. The registry contract is an identity contract. And it is real time with Waku, and they haven't migrated to the Waku network, which is the RL, which also has RLN, rate limiting nullifiers, which helps with spam prevention. This is yet to be upgraded by the Graph. Now, building a radio, building a indexer to indexer communication is less than 30 lines of code. And all of these projects are open source, all of the projects that are mentioned in this presentation so far. And the network is chain agnostic. All right, so I'll do a quick walkthrough of how this looks like in practice. There's a repository that already has the entire workshop that we'll do bifurcated into 9 steps. The repository is this, if you're interested. It's github.com/Danish Arora 099/JS-Waku-stepwise. Could have made it simpler, but bear with me. And the roadmap looks like such. So we'll have, it's got 9 folders, the repository. The first is the setup. So here we'll just set up a boilerplate React plus Vite app. Then on the second folder, we'll set up a Waku node. And so on. At the end, we'll have a full-fledged chat app that also has 2 sorts of encryptions, along with being able to persist your peer ID and whatnot. So let's see what that looks like. So we already discussed, what we'll do is we'll use JS Waku, which is the TypeScript implementation of the protocol. And our approach is going to be just step-by-step building a complete messaging app. And the end result will be a fully functional, decentralized messaging application. So for the first step, we're going to just set up React and React with Vite. And I'll probably have the GitHub repository mentioned somewhere. So this is what it looks like. So the first is setup, and this just sets up a React application. And this is what all the folders will look like. I'm going to try to also open it. So yeah, this is what the step 1 looks like. Not surprised. For the second step, we're going to set up the Waku node. And what that looks like is just installing at Waku/SDK, and then having a TypeScript file that imports two things. It imports the create light node function and waiting for remote peer. Waiting for remote peer is essentially if you wanna wait for your app to make sure that it has connected peers before you start executing the application level logic. So you call create light node, and you pass default bootstrap if you want to connect to the Waku network, or you specify your own nodes here if you do not want to connect to the Waku network and you want to self-host your nodes. You start the node, and then you wait for the remote peer. What that looks like Yeah, so we see here it's trying to connect to the Waku network. So some of these nodes are actually going to be unreachable, and this is normal. We have a little warning at the beginning that says, ignore these, like don't think there's a problem with WebSocket connections failing. So it will try to reach out to as many peers as it can discover. So there's a bootstrap list, and then your node will contact that node, and then it will ask for its own peers. So far, we've been able to connect to 2 peers, which is good. So we know that this works. The second is, so every node that is started with an undeterministic peer ID. Every time you start a node, there's a new peer ID attached to your node, but you can use a deterministic peer ID. And how you can do that is by generating your own public-private key pair and just passing that private key as you're creating the node. If you're familiar with libp2p, this is similar to how libp2p nodes work. Let's see how that looks like. Yeah, so now we have 2 buttons here. One is just using the default behavior, which is indeterministic peer IDs, and then, or using a custom seed, which should ensure that every time the node starts, it has the same peer ID. So yeah, so we used 1, 2, 3, 4 as the seed, and this is the generated peer ID. It ends with VD. We can quickly verify if this is deterministic indeed. Ends with VD. Yeah, so it is the same peer ID. So you can choose to use your own seed to make the peer ID deterministic. And it is an optional step, which is why it's 2.5. Now comes the interesting part where we start defining what data structures and what message types look like when you're using Waku. So with protocol buffers, you can also use JSON. Protocol buffers are just more performant. But since we're building a chat app, and this could literally be anything, and we've seen that, for example, Graph introduces the concept of radios, which of course the data types look very different. For communities, the data types look very different. For the chat app, we'll have 3 things. We'll have a timestamp, we'll have a sender, and we'll have the message itself. And since it's a open, with no recipient in mind, it's an open messaging app. There will be no recipient, but if you're building a one-on-one chat app, you might want to have recipient, and you might want to introduce some encryption schemes to ensure there's a secure channel between the sender and the recipient. Then you then define a content topic that you want to use. It's analogous to PubSub content topics. Then you create an encoder and a decoder with that content topic. For the next step, we'll build out some basic UI components, and let's see how that looks like with the UI components. But this is not something that you want to focus on, at least for this part. Yeah, so what we have here so far is initializing the Waku node with a random seed to make your peer ID indeterministic, or using a specific seed. It starts the Waku nodes. Node starts to connect to different peers it discovers. It has 2 available peers. This is the peer ID. And then this is what the end app will look like. We haven't gone to the part where we start implementing sending and receiving messages, but the data types have been defined. And moving on, we'll do exactly that. The first thing we'll do is we'll see how we can send messages into the network. And note, this is a light client. So this is relying on light push and filter and not relay. And it's as easy as constructing this message that comes from the protobuffer's definition. So we define a timestamp, a sender, and the message. We serialize this message with the protobuffers, and this is an optional step. So you use the serialized message, and you call the lightpush.send API. You pass it the encoder that you had created, and the payload, which is the serialized protobuffer. And that's it. So this is how many lines? Probably less than 20 for the entire thing. Seeing how that looks like. Let's actually do it with filter so that we can actually see also receiving messages, because sure, we'll be able to send messages into the network, but we can't see how they're received. Now to receive messages with filter, we use the subscribe API on the same node object, and we pass it the decoder that we had created. So 3 steps ago, we created an encoder and a decoder along for the content topic. So we use this decoder, we pass it to the subscribe function, and then there's a callback method, and the callback returns a message. You decode this message because it's a serialized protobuffer message. You deserialize it, and you construct it into your own data type, and then you, of course, store it in your UI. At this step, you can now send messages and receive messages over Waku. So the subscription and the callback can be as long as you want or as short as you want. To see how that looks like, all right, we start the node. And I've enabled some debugging logs here, so you'll see what's actually happening. All right, we have 2 connected peers. And we have, let's try sending a message. Yeah, we receive the message, we send the message with light push, we receive it with filter right here. And this is all done without any servers in place. I think we missed the part where we start to see this as obvious, but there is no servers that are responsible for communicating your message. It is all done in a peer-to-peer way. The next step is introducing querying historical messages. Let's say I have a peer here that isn't online, but I still want to see what messages were sent when I was offline, because these messages are only received with filter when the node is online. So let's see if we can try to retrieve the message that we just sent that was, hey from HCC. So we'll go to the step that implements store. And implementing store is also a couple lines of code. It's similar to how filter as an API is used. So you use, there are a couple of methods available. So there's a callback-based approach. There's a promise-based approach. For this, we'll use a callback-based approach. So we'll use query with ordered callback. We'll pass the decoder and then the callback itself. And along with that, you can specify some options. You can have a time filter. You can have pagination. And this is essentially, again, 10, 15 lines of code. Let's see if we can get the node to retrieve our messages. I also sent some earlier this morning, so maybe we can retrieve that. So now the UI has a little button that initializes store on request. So we'll click that button, and it'll try to load historical messages. All right, we'll try that again. You now have 3 peers, or 2 again. All right, classic demo where something breaks. But ideally, what happens here is you retrieve all the messages that were sent out into the content topic, and you see those messages here. And all peer-to-peer networks are inherently unreliable, and there's a lot of work being done to make these systems reliable, but they're not perfect. For the next step, we'll assume that store works. We'll add encryption. And encryption in Waku is, we're a bit short on time, so we'll run through it. Encryption in Waku is application layer. So while Waku suggests some encryption schemes that you can use, it is up to the application what encryption schemes they want to use. For the use case of this demo, we have implemented, can you see that? Yeah, all right. Bigger? All right. So we've written 2 encryption schemes. We've implemented 2 encryption schemes. One's SEs and the other's just symmetric encryption. So the way asymmetric works is you generate your key pairs, you copy this key pair, and then you use this key pair in your recipients tab, and this forms a secure channel so that only the messages that are sent with this particular private key can be decrypted by that recipient. Similarly for symmetric, which is more so used in, which is a different way of implementing the encryption scheme. Let's actually just quickly see how that looks like. So we have one peer that exports these keys. We'll go here and we'll use the peer's public key that we exported here, and then we'll paste it here. And then that's not it. Yeah, so this is the hex for that peer's public key. And this exports, and then similarly, we'll export this guy's public key and import it here. Now this forms a secure channel, so both of these messages that will be sent will be encrypted by SEs, which is the asymmetric form. And you do the same, you just send a message like it's nothing, and no other recipient except this recipient will be able to understand what the message was. And you can use any encryption scheme here, but we have some that you can use out of the box within the library. So it works in a similar way. You generate a private key. Then to get a public key, you call this function. And you create an encoder and decoder respectively with these private keys and public keys. Similarly for the symmetric encryption. And the last step is just enabling and disabling Waku logs. You can do that by setting a key value pair in local storage, which says debug, and the value can be Waku star. This enables all logs in your system. And also using custom nodes if you do not want to rely on an existing fleet of nodes. So the next exercise, if you're still interested, can be adding a group chat. So we already have a group chat, so you can perhaps segregate that into rooms where the same application can now have the concept of rooms instead of just all messages being sent and received by the same person, perhaps reactions, or make it a PWA. There are some resources here that you can refer to. Waku.org is the go-to website. And that's it for me. Thank you. I don't know if we have time for maybe 2 minutes, maybe Anybody has any questions? Yes.
Or is it? Oh, sorry. Is this on mainnet?
It is on testnet. It is the RLN part is on Sepolia testnet, but at the same time, Waku is completely off-chain. If you do not want to use the RLN, which if you do not want to use spam prevention, if you're certain that your end consumers will not be inducing spam, you can use the network. You can self-host your network or be completely chain agnostic.
So if I self-host my network, can I have a closed source of peers that is not connected to the rest of the
Yes,
Waku?
theoretically you can, yes. So that's exactly what Railgun does. Railgun has its own private network. If you're certain that you want to maintain the entire infrastructure, you can self-host your network. Everything's open source at the end of the day.
Okay,
Yeah.
thank you very much.
Of course, thank you for the question. All right, thank you.